In the experiment shown, we have a straight wire. The ends of the wire are connected to a galvanometer that will detect any passage of electric current. The wire is held between the two poles of a magnet. Now the wire is moved downwards by hands cutting the magnetic field lines. The observation is the passage of a small electric current that is detected by the galvanometer as its pointer is deflected to the right. Once the wire stops moving, the electric current also stops. Now if the wire is moved by hands upwards in the opposite direction, the galvanometer will detect an electric current, but this time in the opposite direction, as the pointer deflects to the left. If the wire is moved back and forth parallel to the magnetic field lines, no current is detected. Also, if the wire is placed inside the magnetic field but not moving at all, there will be no current.
Hi guys, the video you just watched is explaining the Faraday's experiment. As a straight coil moving passes through the magnetic field, there's a deflection on the galvanometer. Okay. This shows there is a current flow at that exact moment. This current is called as induced current. So this is basically what this chapter is all about. Let's look at the experiment in details. Okay, you may refer to my summary of chapter 5. So this is on Faraday's experiment. So we have three conditions here. So in this case, we have the galvanometer. Then galvanometer is attached to a coil. Okay, so basically it's a conductor coil lah. Okay, then kita ada magnet here. So our external source of magnetic field comes from the magnet. So this is north, so therefore the magnetic field will be coming out from the north parts of the magnet. Okay, so for the first situation here, we can see that there's no movement of the magnet. So magnet just stays here. So B in coil will be constant. So when the bar magnet is stationary, there will be no deflections on the galvanometer. When there's no deflection, means that there's no current flow in the galvanometer. So for the second part here, so basically we are moving the magnet towards the coil. So B in coil is increasing. Okay, so when B is increasing, so what does it detect? The galvanometer shows a deflection to the left. Okay, as I said, galvanometer going to show the directions of electron motion. Therefore, the current will be in opposite direction. Therefore, so kalau look at here, deflection is to the left, then the current is to the right here. So going to be here lah. Okay, so what happened? We move away the magnet. So we're moving away the magnetic field lines in the coil is decreasing. At the moment we move away our magnet, so the galvanometer shows a deflection to the right. So this indicates that the current is moving to the left. Okay, so deflections of galvanometer shows the directions motions of electron. Hence, it is opposite to the directions of the current. So this is what I said. So basically you can see here, when our magnet is moving towards the coil, deflection is to the left. When we're moving away from the coil, deflection will be in opposite direction. So in the conclusion, EMF is induced. Okay, induced EMF or induced current. Sebab kita boleh guna yang ni, EMF equal to IR. Okay, so basically we're going to measure the induced current. So from the induced current, we're going to calculate the induced EMF when there's a change in magnetic flux. What does it mean by that? Okay, if you look at the three cases here, okay, so for the first part here, this is what it meant by the change in magnetic flux. So remember that definitions of flux is number of magnetic field lines that passes through an area. Okay, so basically we have a coil here. Those three are in the same size. For the first part here, so you can see here, this is 1, 2, 3, 4. So this is, for example, is 4 Weber, 4 magnetic field line that passes through an area. So when we move away, we are pulling away our coil. So our coil is moving away from the bar magnet. So how many lines is that now passes through an area? So there will be 1, 2. So it will be 2 Weber. As there is change in magnetic flux, means that the number of magnetic field lines that passes through an area at the moment it changes, means that there will be the deflections on the galvanometer. There will be current flow in your coil. Okay, so what happens if it is moving towards? It's moving towards the magnet. So now what happens to the punya flux dekat sini? So the 1, 2, 3, 4. So 4 Weber. So at the moment that it changes from 2 to 4, there will be the current flow in this coil that is called as induced current. Okay, as you learned about the experiment that I just explained. Okay, those are the Faraday's experiment. So then Faraday's come up with his own law that states that the magnitude of the induced EMF is proportional to the rate change of the magnetic flux. In other words, to produce induced current, use I ataupun induced EMF, there must be a change in magnetic flux. If there's no changes in the magnetic flux, there will be no induced current. Right? So induced EMF equals to negative N dV over dt. So N normally it depends on number of turns that you have lah. Okay, what does negative means by? Negative indicates that the directions of induced EMF always oppose the change of magnetic flux producing it. Okay, so means that it's going to oppose any changes. That's going to learn about the next law, which is Lenz's law. Other words for induced EMF, we can call it as a back EMF as well. Okay, normally induced EMF will be negative sign lah. Right? So dV will be change of magnetic flux, dt will be change of time. Right? So if the changes happen, at the moment the changes happen, then only the induced current will be produced. If everything will be stable at a very long time, there will be no induced current.